versus functions. Have you ever wished that you could change the weather? One of the technologies used in weather management is cloud seeding. In cloud seeding, microscopic particles are released in a cloud to bring about rainfall. The data in the table show the number of acre-feet of rain from pairs of similar unseeded and seeded clouds. So here we have the unseeded clouds, and here we have similar seeded clouds, and we have the amount of rain in acre-feet. A pair of elements of one set with elements of a second set is called a relation. The domain is the set of the first elements in the ordered pairs, and the range is the set of the second elements in the ordered pairs. We're most familiar with relations in terms of functions, which you should have talked about in algebra. So these topics should be familiar to you from Algebra 2, concepts like relations, functions, domain, and range. So, for example, our pairings of seeded and unseeded clouds, to state the relation of the rain data as a set of ordered pairs, we would just write each of these ordered pairs of the unseeded and seeded clouds. So, as a set of ordered pairs, so usually when we're talking about a set, we use these curly brackets to denote sets. And so within this set, we're going to have ordered pairs, which use parentheses. So the first ordered pair within this set is this first pair of unseeded and seeded clouds. And then our second pair of seeded and unseeded clouds. The unseeded cloud is 4.9 acre-feet, and the seeded cloud is 17.5 acre-feet. And then the third one is 4.9 and 7.7. And so on and so on. You can fill in all of the rest of them on your note sheet, down to the very last one, which is 28.6 and 119. This one down here. And then we close our set with another curly bracket. So how else could we, so also state the domain and range. Your domain is the list of all of the elements in the first unseeded clouds. So I'll put it up here. Your domain is also going to be a set. So we use the curly brackets again. And so it is all of the numbers of the unseeded clouds. In the case of 4.9, which repeats, we only have to write that once. So 1, 4.9, 11.5, 17.3, 21.7, and I'm running out of room, but you should write all of these on your notes, all the way down to the last one in this column, 28.6. And close your set. The range is going to be the set of all of the values in the seeded clouds column. So starting with 4.1, 17.5, 7.7, 31.4, 32.7, all the way down to the last one down here, which is 119. And close your set. How else could we represent this relationship? Well, we could represent this relationship, for instance, by graphing. A lot of the relationships we're going to represent either in tables or by graphing. So for a slightly simpler example, the domain of a relation is all positive integers less than 6. The range y of the relation is 3 minus x, where x is a member of the domain. Write the relation as a table of values and as an equation, then graph it. So x is the domain, and we want this to be all positive integers less than 6. So 5 is a positive integer less than 6. So is 4 and 3 and 2 and 1. Those are all of the positive integers less than 6. The range y is 3 minus x. And so 3 minus 5 is going to be -2, and 3 minus 4 is going to be -1, and 3 minus 3 is 0, and 3 minus 2 is 1, and 3 minus 1 is 2. If we graph these, each of these can be written as an ordered pair with the x and the y coordinates. 3, 0, 2, 1, 1, 2. So each of these can be written as an ordered pair, which we can then graph. So we have some point that is over 5 and down 2, which is slightly off my graph, but that's all right. We've got a point that's 4, -1, 3, 0, 2, 1, and 1, 2. So this is 5. So this is 5, -2, and 4, -1, and 3, 0, and 2, 1, and 1, 2. Now, the other way around, here we have a pair of graphs, and we want to state the domain and range of each relation based on the graph. So, on these graphs, our domain, again, is all the x values. And our range is all the y values. That doesn't necessarily mean just the ones that we see on the graph, because it's possible to zoom in and out of the graph and be able to see different parts of it. So generally speaking, we're going to assume that these lines continue on in the direction that they appear to be going. So the domain, all possible x values, we start, right, this line continues in the negative direction infinitely. Or we are going to assume that it continues infinitely in the negative direction. We have no indication that it doesn't, at least. And the same in the positive direction. We have no indication that it doesn't continue infinitely, so we're going to assume that it does. So our smallest possible x value, right? Remember that the x-axis goes from left to right, so our smallest possible x value is going to be -infinity. And our largest possible x value, we're continuing to infinity on that side as well, it's going to be +infinity. So the domain of this graph, as best we can tell, is from negative infinity to positive infinity. Another way that we can write this is to use this symbol. It's like an R with two lines, two vertical lines. And this means all real numbers. And all real numbers means from negative infinity to positive infinity. And so you can write it in interval notation, which is this. This is interval notation. With the parentheses, sometimes or brackets. Or you can write the weird R symbol for all real numbers. The range is going to be the possible y values. How far does this function or this relation go up and down? And again, we go from smallest value to largest value. So the smallest value, as we are going, as this line goes downward, it goes to negative infinity again. As far as we can tell, this line is just going to keep going down and down and down and down and never stop. On the other end, it's going to keep going up and up and up and up. So our range of this function appears to be from negative infinity to positive infinity as well. And again, you can write that either in the interval notation or using the symbol for all real numbers. For the second graph, our domain, again going from left to right, as we go in the negative direction on the x-axis, our graph appears to go to negative infinity. It's going to keep going to the left forever and ever and ever. So, negative infinity is our lower bound for the domain. And as we go to the right, it's going to keep going to the right forever and ever and ever as well to positive infinity. So our domain is from negative infinity to positive infinity. Now what about the range? Here, this is different because this function, the range, is not all real numbers. So here, the relation does not go all the way down to negative infinity. There is a lowest point, and that lowest point is here at 0. So our lower bound for the range is 0. On the left and the right, it goes upward to infinity, so that is our upper bound. So we would write this in interval notation. There is no fancy symbol for it because it's not all real numbers. It's not from negative infinity to positive infinity. It's from 0 to positive infinity. We use the square bracket here to mean that we include the number, which in this case is 0. The parenthesis means not including the number that goes here, which in this case is infinity. Infinity always gets the parenthesis because infinity is not a number. You can't include infinity. So infinity always gets the parenthesis. But 0 and other numbers will get a parenthesis if we want to go right up to them but not include that number. And we'll get a square bracket if we want to include that number. So here, the range does include 0. There is a point at 0. So we want to use the square bracket. So these relations, you may have noticed a couple of times I called them functions. And most of the relations that we're going to talk about in pre-calculus are functions. A function is a relation in which each element of the domain is paired with exactly one element from the range. So, multiple elements from the domain can have the same output in the range, but one element in the domain cannot have multiple outputs in the range. So you can think of a relation function like a machine. You input the x values, or the domain, and the machine outputs the y values, or the range. If the relation is a function, each input will have exactly one output. Look back at the cloud data. Is that a function? So, go back to the cloud data. Right, here's our cloud data. And so when I input a 1, I output a 4.1. So that's one input with one output. But when I input a 4.9, sometimes it outputs a 17.5, and sometimes it outputs 7.7. So this is not a function. Because the x value, there is an x value that gives two different y values, this is not a function. State the domain and range of each relation, then state whether the relation is a function. So, remember that if our function or our relation is not a line, then the domain and the range are just the lists of all of the possible values. So the domain is going to be the set, we use the curly bracket for the set, of all possible x values. And a set is just a group of things. So for this first example, all possible x values here, we have -3, 4, and 2. And then the range is just the set of all possible y values, which are 0, -2, and 6. And I want the curly bracket there. So there's the range, and the domain is here. This is a function because every input has exactly one output. Every member of the domain has exactly one member of the range. For this next example, the domain, the set of all possible x values, 4, 9, and -9. The range, set of all possible y values, -2, 2, -3, and 3. So there's the range, and the domain is over here. This is not a function because sometimes when you input a 4, you get a -2, and sometimes when you input a 4, you get a +2. So here, inputting the same number gets you two different outputs, and that means that this is not a function. If your relation is represented graphically, you can use the vertical line test. The vertical line test, a relation passes the vertical line test and is therefore a function if you can draw a vertical line through every point on the relation and only hit the relation once. So here I can draw a series of vertical lines through all of these points, and they only hit one point on the relation. So this passes the vertical line test and it is a function. Here, I can draw a vertical line through this relation, and it's going to hit 2 points on the relation. So this fails the vertical line test and is not a function. So if you can put a vertical line anywhere through the relation and hit at 2 or more points, then it is not a function. It fails the vertical line test. In function notation, we read this symbol as f of x, and it means the value of the function f at x. You can also have h of t or g of a or whatever letters make the most sense for the problem. A lot of times we use letters that are what words related to the problem start with. So if I'm having a word problem where I'm graphing the height of an object over time, then I might use h of t, h for height and t for time. It doesn't actually matter what letters you use. It's just important that each function assigns exactly one member of the range to each member of the domain. To evaluate a function for a given value, all we have to do is plug that value in. So if f of x equals 3x to the third minus 7x squared minus 2x, and we want f of 4, right? This is f of x. We want f of 4. We're going to take the 4 and plug it in for x. So if f of x is 3x cubed minus 7x squared minus 2x, f of negative 4 is going to be 3 times negative 4 cubed minus 7 times negative 4 squared minus 2 times negative 4. Negative 4 cubed is negative 64 times 3 is negative 196. 192, I think. Why am I doing this when I have a calculator? 3 times negative 4 cubed. Yes, negative 192. Minus 7 times negative 4 squared. Negative 4 squared is 16. 7 times 16 is 112. And then minus 2 times negative 4 is going to be minus negative 8, which is plus 8. And when we add those up, that's 304, negative 304 plus 8 is negative 296. Similarly, g of 9, if g of x equals the absolute value of 6x minus 77, we're going to take the 9 and we're going to plug that in for x. So g of 9 is going to be the absolute value of 6 times 9 minus 77. 6 times 9 is 54, minus 77 is 23, negative 23. And when you take the absolute value of that, that is positive 23. H of a, if x equals 3x to the 7th minus 10x to the 4th plus 3x minus 11, again, we're just substituting a in for x. So if this is h of x, then h of a is 3a to the 7th minus 10a to the 4th plus 3a minus 11. We just turn all of the x's into a's. J of c minus 5, if j of x is x squared minus 7x plus 4, plug in for x. Right, so c minus 5 squared minus 7 times c minus 5 plus 4. We do want to simplify this. For this c minus 5 squared, we need to FOIL this. This is not c squared minus 5 squared. We need to FOIL c minus 5 times c minus 5. So we multiply the c's together and get c squared. We multiply the outer terms, minus 5c. The inner terms are also minus 5c. And the last terms are plus 25. So we're going to get c squared minus 10c plus 25. Now we're going to distribute this negative 7. That's minus 7c plus 35 plus 4. And then combine our like terms. We've got a minus 10c and a minus 7c. That's minus 17c. And a plus 25 and a plus 35 and a plus 4, which is plus 64. When you're given the equation of a function, but the domain is not specified, we assume that the domain is all real numbers for which the corresponding values in the range are also real numbers. So, looking at this f of x equals x cubed plus 5x over x squared minus 4x, what can we not have? We can't have the denominator equal to 0. You can never divide by 0. It doesn't work. So, the domain is everywhere except where this denominator equals 0. In order to determine where this denominator equals 0, we're going to factor it. So x squared minus 4x, we can factor out an x and make this x and x minus 4. So this function, if we were to set this equal to 0, this denominator is going to equal 0 when either x equals 0 or when x equals 4. So our our domain is everywhere except 0 and 4. To write that in interval notation, we want to include all numbers except 0 and 4. So starting at negative infinity up to our lower number, which is 0, we don't want to include 0, so we're going to use the parenthesis, not the bracket. And then we want another part that starts from 0 and goes to 4. And we don't want to include 4. And then we've got another part that starts at 4 and goes to positive infinity. So that covers all of the numbers from negative infinity to positive infinity, but doesn't include 0 or 4. And then in interval notation, we put a u in between these to say that these are all together. They're all part of the same interval. In part B, g of x equals 1 over x minus 4. We know that the denominator can't equal 0. So the square root of x minus 4 can't equal 0, which means that x minus 4 can't equal 0, which means that x can't equal 4. However, we also have a square root, and we know that we can't take the square root of a negative number. So we know that this part that's inside the square root has to be positive. So for what values of x is the part in the square root positive, greater than 0? That's for all values greater than 4. Not equal to 4, because that would give us the denominator of 0, and not less than 4, because that would give us values that are negative, and we can't take the square root of a negative. So all values that are greater than 4 in interval notation is going to be from 4 to infinity. Again, with parentheses, because we don't want to include 4. Our process for finding the domain in general is that we start by assuming that x equals all real numbers from negative infinity to positive infinity. And then we're going to find the things that x can't be. So x can't be anything where we have to divide by 0, anything where we have to take the square root of a negative, anything where we have 0 or a negative inside a log, which we'll talk about later on in the course, and trig functions have special domains. We'll talk specifically about domains and ranges of trig functions when we get there. But right now, the two that you need to worry about are these two. And then we write down the domain minus the holes. So going from left to right, starting at negative infinity, we go until we get a hole, write the endpoint for that, and then start at the next available point and go on skipping the holes until we get the entire domain. And that's it. See you again next time for section 1.2.